Welcome to the SEI Podcast Series, a production of the Carnegie Mellon University Software Engineering Institute. The SEI is a federally funded research and development center sponsored by the U.S. Department of Defense. A transcript of today's podcast is posted on the SEI website at sei.cmu.edu/podcasts.
Welcome to the SEI Podcast Series. My name is Suzanne Miller, and I'm a principal investigator in the SEI Software Solutions Division. Today, I'm joined by Dr. Thomas Scanlon, who leads the data science program in the SEI CERT division. Dr. Scanlon recently participated in the workshop on cybersecurity of quantum computing, co-sponsored by the National Science Foundation and the White House Office of Science and Technology Policy. Participants in the workshop examined the emerging field of cybersecurity for quantum computing, which is the topic of today's podcast. Welcome, Tom.
Thanks. Great to be here.
So you've done podcasts with us before, and we will include links to those for our audience. But for those members of our audience who haven't listened to your previous podcast, could you start by just giving us a little bit of what you do here at the SEI and what's the best part about your job?
Sure. So I'm currently the technical manager for the CERT data science team. And so we're looking at areas where cybersecurity and data science intersect. So that's both protecting AI and ML systems and using AI and ML systems to solve cybersecurity problems. As part of my team, we also have quantum computing in our area, which is what we're here to talk about today. And so we're looking at a few different aspects of quantum computing, which we'll talk about today.
Yes, and especially the cybersecurity aspects of it today. So we have done previous podcasts on quantum computing with various members of your team. For those in our audience who haven't heard those podcasts or haven't heard of quantum computing, we will include links in our transcripts. But can you give us just a brief overview on quantum computing and how does it differ from what we might call traditional binary computing?
Sure. So typically in relation to quantum computing, we say classical computing to talk about the traditional computing you mentioned. But in a classical computer, information is stored as a 1 or a 0 and as bits. And those bits are reflective of a physical property that a transistor has current to it or not. And so with each bit, we can represent one piece of information. The bit is either on or off. In the quantum world, we use something that's called a qubit. And that can store more information. And I have a little bit simplistic example, but it really resonates with people. And so I think of flipping a coin in the air. And so if you flip a coin in the air and it lands heads up or tails up, you can then measure it heads or tails. And that's similar to measuring a 1 or a 0 in a classical computer. However, if you can measure that coin while it's flipping through the air, it can be in a state of 1 and 0 at the same time. And that's sort of what's going on in a quantum computer. We have something we call superposition. And in superposition, it allows the qubit, which is the term we use, allows the qubit to represent a 1 and 0 at the same time. And then another property of quantum computing that allows us to store more information is this concept of entanglement. But in this example, imagine you could flip 2 coins at the same time and measure both their states at the same time in relation to each other. And so now you can store more information. And as you add qubits, the ability to store information grows exponentially. On a traditional computer, it grows linearly. So as you add bits, it grows linearly. But in a quantum computer, it grows exponentially as you add qubits.
So that's really the attraction of quantum computing, is this ability to store more data related to attributes that we care about that we're using in our software. And that's one of the things that I don't know that that really comes through to a lot of people, is that we actually get some advantage from quantum. It's not just a toy. Ooh, isn't that cool that we can have superpositions and entanglement? But it actually has meaning in terms of our ability to include more information. And as we get into the AI and the ML and the big data, that becomes relevant, right?
Yeah. And so it allows us to represent more data. And so it allows us to do calculations on it. And so what we talk about is that in classical computers, there's untractable problems. Sometimes you might hear the term NP hard problems, but problems that it's not that they can't be solved. It's that they can't be solved within human reasonable timescales with the computers we have available to us today, due to the potential of quantum computers to process information much faster and much more information. That'll allow us to solve problems that would be untractable today.
So talking about sort of the bigness, big data, data science is your specialty area. Where do quantum computing and data science explicitly converge?
So there is a field of research on quantum AI and quantum machine learning, and really, anytime you're doing data science, you most of the time anyway, you have a lot of data that you need to work on, and so that's why you're using AI or ML in the first place is to process a lot of data and make a prediction about something, and so with the power of quantum computers, there are machine learning algorithms, different approaches that you might not try today because you couldn't get your results in a reasonable time. If you have that power of the quantum computer, that can really accelerate the types of problems you can also solve in the AI and ML world. And so there is a relation. One of the areas that research is looking at is there is quantum computers are used now and probably will in the near future, is what we call a classical quantum hybrid. And so you're still going to use a classical computer to do a lot of tasks, and then the quantum computer will be more of like a co-processor where you'll farm out the calculations. And given that, when you're talking AI and ML and lots of data, there is a bandwidth problem to be solved on how do I get all this data from the classical world to the quantum world. And so that's one of the many challenges in the quantum computing space that folks are working on.
Okay. So with more data come more threat surfaces, right? Attack surfaces and threat vectors. So you talked about this in a recent blog post and the aspects of quantum computing that make it a potential target for malicious actors. How do the attack vectors in quantum computers differ from attacks that are leveraged against classical computers?
Yeah, so this is an area that, as you mentioned, I've been working with some other researchers around the country on. The idea is the most press that quantum computing is getting is threats it may represent to cybersecurity, the ability to, break encryptions and do things like that. But there hasn't been as much discussion on how to protect quantum computers. And anyone who works in security, we always want to be in sooner, right? And so there's network protocols in use today that weren't designed with security in mind. They were designed with functionality in mind. And since we're sort of still at the advent of quantum computing, now is the time to start thinking about security and really get security concerns addressed up front. And so some of the differences are, so a lot of the threats that are in classical computers will also be in quantum computers, first off. But some of the things that are different is giving the amount of resources it takes to perform a quantum calculation and get a result. The protection of that result is going to be even more heightened than normal. So in a classical world, if I could get access to your data, I could probably recompute results on my own and draw conclusions. But because of all the horsepower and resources that go into creating a quantum result, I'm gonna want to take your result and not your
I don't want to have to recreate the data. Yeah. Okay.
And then another difference is the sensitivity to the physical environment in current quantum implementations, and so it's more sensitive to heat and noise in the environment, and so I can perform like essentially a DDoS attack or some type of attack on your quantum calculations by attacking your heating and cooling systems. I can attack the integrity of your quantum calculation by introducing noise, and so there are some different attack vectors for quantum computers that need to be researched and solved.
So, given that, how do people using quantum computers protect themselves from these types of attacks? Do we have strategies in play already, or is that sort of something that was really part of what you were exploring in the workshops?
So that's what we're exploring in the workshops, and so we looked at things that have been done for inspiration, and so there are parallels to high performance computing and the protections for those that would apply to quantum, but there are also some things that need to be uniquely developed for quantum, and so this gets into the 6 areas that we outlined in the blog. But for instance, there isn't for existing quantum implementations the ability to monitor processes in progress the way there is for a classical computer. So I can pull up and look at CPU utilization and figure which jobs are using which horsepower and even sort of infer what types of activities they're doing. In the quantum world, we don't have that tooling and instrumentation right now. So that's one area, it's one of those 6 areas of research. Another is...
And that area, I mean, that applies not just to security, but just to understanding whether what you've asked the computer to do is taking up too much bandwidth and too much resource. So you need a task manager, in the Windows equivalent world, so that you can understand multiple aspects of your quantum computing. But security certainly would be one of them.
Absolutely. And also, another attack that someone might want to perform on a quantum computer is to sort of just hijack your quantum computing power. And so I don't have, quantum computing power of my own. So if you think, analogy to like how botnets work in the current world.
Yeah.
So I want to hijack your computing power and perform my calculation. Currently, there's no, reliable methods to say what algorithms the quantum computer is working on. And so, you wouldn't necessarily know that some unauthorized algorithm is being executed in your quantum. And so these are all the areas of instrumentation and control systems that we definitely need research in.
What are a couple of other areas? You mentioned 6 areas. So we've got the sort of botnet. I'm going to hijack your computing power. I've got the I'm going to mess with your HVAC. I'm actually going to try and hijack your result. What are some of the other areas that you're working on?
So 2 related areas that we called out in the workshop and that are described in the blog is creating formal methods for safe and secure quantum computing systems, and developing the tools needed to verify quantum algorithms. And so there's a relation there. But as you know, there's a lot of work in formal verification of software and applying formal methods. So, just like I talked about earlier, we have parallels between high performance computing and quantum. We have a lot rich history to draw on informal methods of verification of software systems, but we need to grow and adapt those for the quantum space so that we can, provably prove things about quantum computers.
One of the challenges of that has got to be that at least most of the formal methods that I'm aware of have really been focused on deterministic kinds of proofs. And in the quantum world, you're dealing with probabilities in many of your sort of outcomes are probabilistic. Is that one of the challenges in adapting formal methods?
That is a challenge. Quantum computers can solve deterministic problems.
Of course, yes.
Yeah, and so
but they can also solve the probabilistic ones that other classical computers can't.
Right, and so that's part of the discussion is what formal methods will apply more directly, where are areas for future research, and maybe if there are areas where we can't develop formal methods, what's the best we can do to try to maybe probabilistically prove a property, and so that's an area of research too.
Okay, so if I'm trying to work in quantum right now, probably security is not at the top of my list of things I'm worried about, even though I should be. But what are the sort of first couple of things I should be doing to protect my system from what we have available to us now?
Yeah, so I do look at the quantum cybersecurity that we're talking about today as a little bit of a future task for users of quantum computers. So it's something that needs to be addressed now by developers and researchers and implementers. But if I'm an organization that wants to leverage quantum computing or be positioned to leverage it in the future, one of the first things that I tell folks to do is develop quantum use cases. And so in your organization, talk about problems you have that a quantum computer might be able to address. Talk about where you would get data to address those problems. Talk about what success would look like in those use cases. A lot of typical use case development things. And then as you work those quantum use cases and you think about how you would use quantum in your domain, then you can start to ask, okay, if I do use quantum in my domain, what do I need to protect? How do I protect it? And then you want to start having the security discussion now for the same reason. If you're a pharmaceutical company and you use so one of the areas for promise for quantum computing is in chemistry.
Yes.
And so you use quantum computing to develop, some new drug, or in biology, some new molecular combination or something like that. Now you come back to those questions I raised earlier. Well, how do I protect this result? how do I be able to verify my results?
Right.
How do I
Right.
protect my calculations? And then so you also get into some regular software engineering problems, like how can I recreate my results? But if you can recreate it, that also helps speak to the security or reliability, right? So,
Right.
but so for the average organization that's not a firm developing a quantum computer, I think you wanted to start with quantum use cases and say, what would we do with quantum?
Right.
And what are realistic problems for quantum and not? And that may be somewhere you want to, consult with someone that knows more about quantum to say, hey, these are good use cases, or these wouldn't make sense.
Yeah. Well, and to the security point, as you work through those use cases, you start to get an idea of what are the assets I need to protect, as you said before. Is it the data, or really is it the result? Is it the algorithms? And then how do I go from there?
Yeah,
So,
and so another part of that for like an end user of quantum computers is it's fairly feasible that when quantum computing becomes available to a typical organization, they're going to use it as some type of cloud service, either cloud
okay.
proper or cloud, as a concept, but it's gonna be like a shared service, right?
Sure.
Because most organizations in the near future, or even the sort of mid future, aren't going to be bringing their own quantum computing environments in house. Some will,
Right.
but most probably will not. They will just want to use the processing power, and so then you have to talk about how do I get my data in and out of there? What are my multi-tenancy requirements? So who am I willing to share this computing cloud with?
Yeah.
Some of these issues again that are sort of relevant to cloud computing now, but do it in a quantum context.
Okay.
Will someone else's use disrupt my calculations? Those are questions you might want to ask a provider.
Right. Yeah. Okay. All right. Those are all good questions. I think people appreciate hearing those. But there's a little bit of, on the end user side, sort of stay tuned. We're really at the beginning of this. And so we don't really have the frameworks in place like we have for classical computing for, security, cybersecurity folks that are trying to do the protection at the endpoint.
Yeah, and so we're entering an era that in the quantum computing literature we call NISQ era, which is near term intermediate scale quantum computing.
Okay.
Noisy intermediate quantum scale. And so the idea is it's intermediate scale. So we have some quantum computing power, we have some qubits available. We're nowhere near realizing the full potential of quantum, but we can do quantum calculations. And then the noisy piece is that the calculations may still be subject to destabilization and different things. And so we'll have to pay attention to error correction and integrity of the calculations and things like that, so that they won't be provably 100% reliable every time.
Right.
But they're good enough that we can actually compute some things. And so as that NISQ era comes, that's when organizations might want to start to be able to see what kind of problems they can get into solving.
Yeah, this is exciting. And so this is not the only thing you do. You're looking at data science in general. What is next for you? What are you working on now that we'll be able to talk to you about in 6 months or a year?
Yeah, so I neglected to ask one of your opening questions, which is what do I enjoy working at the SEI? And so definitely what I enjoy is the variety of work and challenges that we get to address here. And so I have a lot of challenges that are on my plate that we're working on. But one, not necessarily related to quantum computing, but could be enabled someday by quantum computing, that I've been doing some work in that I'm really excited about, is measuring trust decay and trustworthiness in a variety of systems.
Oh, interesting.
And so the short of that is there's a lot of attention being paid to zero trust right now, for instance. And in zero trust, what we really mean is zero implicit trust, right? So we don't trust anything by default. At some point, though, we do trust something after we put them through an auth process. But how does that trust decay over time? So, I've authorized a device on a network, or you as a user, sort of the naive approaches to trust decay that we use now is basically lapse of time, right? After so long, I'm going to make you re-authenticate. Or maybe if you're like on a VPN,
you do.
On a VPN, maybe I'll make you, if you drop, I'll make you re-authenticate or something like that. But we're looking at this in IoT worlds and 5G communication worlds. and say, okay, someone's coming on and off the 5G network. When is it time to make them re-authenticate? And so we're developing probabilistic guesses of somebody is who they say they are or they're not. And that can be based on latency, battery power, how often you're on and off the network, physical location, a whole variety of factors. And we're applying this in different domains and saying, can I make some probabilistic trust assertions about whether you belong on this network or in this system or not?
Okay. All right. That's interesting. I work in some areas where that would be very relevant. So I'm sure a lot of our listeners do. So that will be something I look forward to talking to you about in the future.
Absolutely. That would be great.
I really want to thank you for talking with us today. This area of quantum computing, you talked about us being on the cusp sort of a new era. And it does feel like that, between the quantum computing, some of the the sort of reduction in cost of high performance computing, sort of all the, AI, ML, large language models and everything there's a whole bunch of things coming together. And I think quantum computing is going to be one of the enablers for some of these other things that we're starting to get to know what we can do with, to actually be able to be used productively. So this is really important, and keeping that secure is very important to all of us. So I think most of us have got the message that any new thing, we've got to get secure.
Right.
And quantum fits into that. So I'm going to be looking forward to what you do in this area in the future. We have the podcast on quantum computing. We have your blog post on cybersecurity. All of that material will be in our transcript today. And I want to remind our audience that our podcasts are available lots of places: Spotify, SoundCloud, Stitcher, Apple, Google, you name it, and the SEI's own YouTube channel. So if you like what you see and hear today, give Tom a thumbs up. I know he'll appreciate it. So I want to thank you again for joining us, and everybody have a good day.
Thanks for joining us. This episode is available where you download podcasts, including SoundCloud, TuneIn Radio, Google Podcasts, and Apple Podcasts. It is also available on the SEI website at sei.cmu.edu/podcasts and the SEI's YouTube channel. This copyrighted work is made available through the Software Engineering Institute, a federally funded research and development center sponsored by the U.S. Department of Defense. For more information about the SEI and this work, please visit www.sei.cmu.edu. As always, if you have any questions, please don't hesitate to email us at info@sei.cmu.edu. Thank you.